So we're now in the last section in Chapter 10, Section 10 in Chapter 10. We're going to graph logarithms using tables, and we're going to graph logarithms using their inverses, namely exponentials. So using what we learned in Section 9. So first off, let's remind ourselves of what the inverses are. So if I ask you what the inverse of the log base 2 of x is, you'd have to say 2 to the x is the inverse function. Similarly, if I asked you what the inverse of 7 to the x is, well, the base is 7, so the inverse would be log base 7 of x. So we're going to graph y equals log base 2 of x using its inverse. The inverse of the log base 2 of x is 2 to the x. So we're going to make a table. Here's the table copied and pasted for y equals 2 to the x. So remember how we made each of those. Now notice that the inverse swaps the roles of x and y. So where I see an x in the inverse function, I'm going to see a y in the inverse function. So there's the x's becoming y's, and similarly, where I see a y, that is an output in the inverse function, I'm going to see an x in the function itself. So we're going to see those same numbers. In other words, we're swapping x's and y's. So here's the graph of log base 2 of x. We can see a little bit more of it. We can see that it is the inverse of y equals 2 to the x. Similarly, if you are graphing log base 1/2 of x, you can remember that the inverse of that is the halving function. So here's the table from the halving function. Our x's are going to become y's, so we're going to copy them down here, and what do you know? They become our y's. The y's become our x's, and so we've got a table. When we use that table to graph the log base 1/2 of x, we see that it is the inverse, that is the mirror image across the diagonal of the halving function. Okay, now we're asked to use the graph of y equals 2 to the x to graph its inverse, that is the log base 2 of x. And to do that, we're going to notice that any point on 2 to the x has a matching point where you swap x and y on the log base 2 of x. So here's a point, -1, 1/2, and notice that on the graph of the log base 2 of x, we have the point where x and y is swapped, 1/2, -1. Here's the point 0, 1, and on the inverse, 1, 0. Here's the point 1, 2, and on its inverse, 2, 1. Finally, we're asked to identify each of these graphs by using the base. So we can compare these graphs and see that one grows fastest and one grows much slower. So for example, this uppermost graph, k of x. So it must be the inverse function of the graph that grows the slowest. And 1.3 to the x grows the slowest among the bases that we have here. The next smallest base is 2, and that's going to be the graph that grows the second fastest. So that's going to be our g of x. Natural log has a base of e. E is bigger than 2, so it's our next graph, h of x. And then the one that grows the slowest is the inverse of the 10 to the x, which grows the fastest. If we graph y equals 2 to the x and the log base 2 of x on the same axes, we can see how they're related. They're a mirror image across that main diagonal, that line y equals x. That's the same line y equals x that we used when we were graphing the inverse given a function. So that's the same mirror image, a little bit more difficult to see when it doesn't cross the line because each of these points is a mirror image across it. So those dashed lines showing us how each point is connected to its mirror image. In other words, each point is equidistant from that line. And of course, each of these points, that's a mirror image across the main diagonal there, is also found by swapping x and y. So the point xy on one of these has a mirror image on the other with the point yx. That completes chapter 10.